Thank you. Hi everyone, I'm Safa. I'm working in Turkish aerospace industry. I hope everything is okay out there. So today I'm going to talk about blade element momentum integration to SU2. First, we start with what is blade element momentum theory. After that, how we calculate the necessary variables for blade element.
Oh, Safa, we lost your audio. Safa, can you hear us? We lost your audio. Ah, there, you're back. Okay. We lost about the last 20 seconds, so please, if you could repeat.
Moment.
Safa, we're still having trouble. Is it possible for you to turn off your video just to increase bandwidth a little bit? I see you have your video on.
Is that okay now?
Yeah, it seems a little bit better. Go ahead.
Okay. After, in the conclusion, we will talk about what we get from the BEM, blade element method. So, in a rotor CFD analysis, you need to a complex mesh structure in each blade with boundary layers. So blade element momentum theory is alternative way to do it. Basically, it splits the blade elements into small parts which hold blade elements, and you assign the 2D airflow theory, and you calculate the aerodynamic forces acting on that element. So how we calculate the aerodynamic forces? Let's start with induced angle. Induced angle is an angle between normal velocity and the tangential velocity. This relative velocity become from two different velocities. One of them is blade velocity caused by rotor rotation, and other velocity is, as you know, free stream velocity. We have to calculate the effective angle of attack first. So effective angle of attack becomes from three different angles. First term is induced angle, as I mentioned previous slide. The other is blade twist angle, which is a design parameter, and the other angle is control angle, which is collective and cyclic angles. This gives us the effective angle of attack, and in simple lift and drag formulation, we multiply dynamic force with lift coefficient and drag coefficient. In that formula, in the BEM method, we calculate CL and CD, lift coefficient and drag coefficient from 2D data. And you can see the first term as it's called solidity. Solidity means blade area over actuator disk area. So you can multiply with solidity, and you get each node of aerodynamic force in each node. So we can calculate this lift and drag from 2D data, obtained from 2D data, that forces acting on airfoil frame. So we have to transform into our coordinate system. In a basic transformation like this, and we get normal force and tangential force. That angle is induced angle, as I mentioned before. We can calculate the rotor forces acting on actuator disk like this. And we have to implement this force into SU2. So how we do it? In momentum equation, first term is change in momentum due to time. After that, mass term, pressure term, and stress term following that. we calculate the force of the rotor. So taking integral around actuator disk, we can calculate the blade element momentum term, and we can add this momentum equation. This term is generated by rotor, so we can calculate the flow variables. What we have to do for this case, you have to split your mesh into across the band plane. So calculated momentum variable will be added to the flow from this intersection. You can add more than one rotor to this intersection, but just be careful about making a fine mesh around the rotor for better results. You can see the streamlines coming from the actuator disk. There is no solid body in here. There is only interface, and you can see the effect of the rotor. In this method, this code requires a rotor model input file, which includes how many rotor do you have, what is the radius of the rotor, rotor coordinates and control angles, and data of the blade elements, blade sections, such as chord twist location of these sections. After that, we do a validation case on Robin. Robin extended name is rotor body interaction, which experiments made by NASA. You can see the reference. First term in here is advance ratio. Advance ratio means the free stream velocity over the tip velocity. Tip velocity is calculated from rotor rotation, RPM, and free stream velocity, higher advance ratio means higher flight, forward flight in that velocity. And we can calculate thrust by thrust coefficient. That variable is solidity that I mentioned before, blade area over disk area, actuator disk area. Experimental thrust calculated from this variable, and this collective pitch angle gives us the sections twist. We calculate the section twist from this variable. That two angle gives us the lateral and longitudinal cyclic pitch. As you know, in helicopter systems, in left side, air comes from the airfoil from trailing cage, and in right side, air comes from the airfoil to the leading cage. So there's difference happened because of the free stream. You have to change your pitch angle for generate equal lift in each side. So we analyze these cases. First, you can calculate force components, momentum components, torque and power in runtime. The important part is Z-force, which is thrust. In experiments, it's calculated as 979 Newton, and we calculate 980 Newton with the SU2 integrate method. In this figure, you can see the Z momentum. We set the upper legend to 0, so you can see the bluish colors are in the bluish colors. Flow direction is going to the negative Z direction. I mean to the rotor body, Robin body. So there's pressure distribution. After that, we continue to validation to CP check, experimental CP check. Next graphs, NASA set the probes to these sections. So we will be plot the CP section in that sections. The first one is Y normal. It's almost in the center line. The others are in the X normals. So in the first graph, you can see the trend is the CP is fitting with the experimental data, and also the data almost crossed each other. In the other sections, there is a little bit difference in SU2 BAM method and experimental CP data. So we checked another implementations to the other CFD solvers. They have same situations actually. I add the other results, the other CFD integrated CFD results to the other slides, and hide it. You can see it when it's published. And also we multiply CP with 100, so better visual. So there is so little difference between BAM and experimental data. We run all these three cases. I also hide other cases. You can check the other cases CP if you want when the presentation is published. Now you can see in case 1 and 3 there is so accurate result in the trust. In case 2 there is a little bit higher error in the trust. That's because of in case 2, you can see advance ratio is a little bit small. That means it's almost equal to 0.09 mAh. So there is a little bit error in here, but it's still acceptable. Also, in classical BAM method, BAM assumes the flow variables are constant, such as density or other velocity components. But in this method, we take these variables from the CFD. So it increases the accuracy. So we get low error in the flow. So blade element method, as you can see, provides precise and accurate analysis in aerodynamic forces. It's efficient way to solve rotor system. As I mentioned, rotors requires more complex mesh structures around each blade. You don't need to you don't need such as complex mesh systems in actuator disk method, actuator disk BAM method, and also you have to run your rotor bodies with rotating domain in other CFD methods, and it has to be unsteady case, but with this actuator disk method, you can run your analysis in steady conditions. It's also flexible. User can be customize their cases with only changing the rotor model input file. And validation studies successfully carried on Robin case. This actuator disk method, BAM method, can be used in different fields such as helicopters, wind turbines, aircraft propellers, distributed propulsions, and also we are using this method in our company's aircrafts, and the results are really reliable. So I hope everything is clear, I hope. Thanks for listening. Now I can get the questions if there is.
Thank you very much. There's a question.
Thank you.
Yes, I was wondering why you split the domain for the test case in two, why you decided to run multi-zone.
Question was why you split the domain.
Which mean I couldn't hear?
The question
One more
was
time.
why you are splitting the domain into two pieces.
Because we are adding the momentum variable into this interface. We need to interface mesh and we add this calculated moment into this node of the interface. And also we think about the optimization cases. If you want to add more than one rotor into one section, you can do it and changing the coordinates. Maybe we can use it with only one domain, but if we do it like that, we can change the center of the rotor. So like this method, we can change the rotor in one plane.
Okay, thank you. Yes. Are there further questions? That's not the case, so let's thank the speaker again.